So today I'm going to speak about fermions and their connection with random matrices. So the details of what I'm going to be presenting are given here. Okay. So this was the work done with some colleagues in France, Satya Mujumdar, Gregory Scher, and Pierre Ledoussal. So I'll give some brief background and motivation and present some results on 2D fermions, and then present some connections with things like orthogonal polynomials, random matrix theory, and so on. So just to motivate, there has been great experimental progress in cold atoms. You can confine them in various kinds of traps. You can have them in different spatial dimensions. You can tune interactions. You can have different temperatures and number of atoms. You can measure the collective density by absorption imaging techniques. So you have trapped cold atoms and you can measure the collective density. And very remarkably, you can also resolve the measurement at the level of single atoms, which is the quantum gas microscope. You can study time dynamics and so on. So it's an excellent platform to study quantum and statistical behavior in many body systems. So today I'm going to speak about non-interacting fermions and how Pauli exclusion can lead to highly non-trivial spatial profiles and correlation. So this is my schematic. So you just imagine, just to set the stage, you have fermions in one dimension in a harmonic trap. So you would imagine that this blue dome here is the emerging collective density. And you have these fermions in a harmonic trap, and this is the schematic. And these are some nice experiments where you can literally, as they say here, you can do site-resolved imaging of individual fermionic atoms. Okay, so generally to study collective behavior, when you have these kind of fermions in traps, things that is reasonably promising is some sort of local density approximation, where you sort of avoid microscopic approach and you have some density-based theories. But usually these don't work when the densities are small or when it's at the edge. So this has been already recognized by well-known people, where they say density-based many-body theories is inappropriate near edges. So here we are going to start with a more microscopic viewpoint by looking at the Schrödinger equation. So the philosophy is that we study fermions in traps or some versions of those. Okay, so let me start with a simple example. So you have, imagine you have fermions in a 1D trap. This is the harmonic oscillator, and you keep putting spinless fermions respecting Pauli exclusion principle. And then you ask, how do they arrange themselves in space? So you have this energy level diagram, and I keep loading fermions respecting Pauli exclusion, and these are spinless fermions. So this is a very simple problem to state, and then you can calculate its many-body ground state wave function, and then you can calculate quantum probability distribution, which is the joint distribution of positions of fermions in the ground state. Okay, so this is basically determinant of some polynomials, and you can write it as a van der Waals determinant. So this is how the joint distribution of positions of fermions look in the ground state. From here, you can extract other things like density and so on. But once you look at this, you can immediately see that this is exactly analogous to the joint distribution of eigenvalues of a GUE random matrix. So because of this deep connection between fermions in a one-dimensional trap and random matrix theory, you can say a lot of things about these cold atomic systems. You can immediately say that the average density is the Wigner's semicircle law. You can ask about the distribution of the rightmost trapped fermion and so on. So this connection with random matrix theory is useful in multiple ways. One is you can actually lift very well-established results of random matrix theory and use it to explain cold atomic systems. Another is you can use these cold atomic systems as some sort of a test bed to verify some random matrix calculations. Okay, so this is the thing. So this is basically the big picture, where there are things like Wigner's semicircle. There are things like zeros of Hermite polynomial, and this well-known problem called the Stilcher's algebraic problem, where, for example, zeros of Hermite polynomial will form a semicircle, and solution of this algebraic equation also forms a semicircle, and so on. But then these are all deeply connected to things like random matrix theory, fermions in 1D trap, and also other things like generally the Dyson's log gas and some integrable models. So what we are interested is in some sort of higher dimensional generalizations to this. And so natural questions to ask is what happens to fermions in higher dimension? Is there a random matrix connection? Are there any orthogonal polynomials? And so on and so forth. So one natural thing that comes to mind is, I spoke about fermions in a 1D harmonic trap. What about fermions in a 2D trap? So then what happens is that you can do some exact calculations and show that it forms a dome. Just like in a 1D trap, you get a semicircle. In 2D trap, it forms a dome. But interestingly, there is no random matrix theory. So on the other hand, you know that once you start talking about two-dimensional fermions, you need some non-Hermitian random matrix, because you want to study complex eigenvalues and ask whether complex eigenvalues of any non-Hermitian random matrix, will they start looking like fermions in 2D? And it turns out that the well-known non-Hermitian random matrix theory, which is the Juniper class, actually does not have a dome-shaped density of states. The density of states, the eigenvalue density is just a disk. So immediately generalizing it to higher dimension makes it difficult. But what has been achieved is, it has been shown that if you take these fermions in a 2D trap and rotate it, then you can show that the density of fermions under some settings is actually mapping to Juniper random matrix of Juniper class. So non-Hermitian Juniper matrix is, approximately speaking, you take elements, you draw it from a Gaussian distribution, don't care about hermiticity. Calculate their complex eigenvalues, plot them. You will see a disk of radius root n, a flat disk. And the fermions in this kind of setup will actually form a flat disk. Okay, and here the story is slightly more complicated than the harmonic oscillator, where you have this single particle spectrum, but then I keep again loading fermions and asking how they would look in space. So this is the question. You fill it in the energy level diagram and ask how is it spatially local? How does it look spatially? So the answer is that the many-body probability is basically exactly that of the Jin-Ui class. So basically the program seems to be the following. You solve the Schrodinger equation whenever possible, and you start filling fermions respecting Pauli exclusion principle. Again, this is zero temperature. Things become a little more complicated when you have finite temperature. And then you ask how they would look for any finite n, and then you derive some large n results and try to make connections with random matrix theory. So we considered this kind of model with a repulsive, with a harmonic trap with some repulsive central potential. And it turns out that this is exactly solvable in terms of Legler polynomials. The details are not important. Here, you can think of this as the trap, and this is a two-dimensional fermionic system that is rotating. Okay, so it turns out that this model has a very interesting energy level diagram, and I do the same thing. We sort of start filling fermions. So you start filling it from here, you fill it here, but then when you have extra fermions, you can't start filling here. You have to go to the next band. So you start filling it from the lowest energy onwards, then you fill it in the next band. Then you keep going here, then you fill the next band. And then you ask, how does it look in space? And it turns out that it has this very interesting wedding cake structure. So it turns out that if you have some K bands, you have this nice, this is the density of that fermionic system where you have this nice wedding cake structure. So if you want, you can think of it as 3 Juniper disks on top of each other. But so this is how it would look. So what I wanted to say is that it is not entirely obvious how things would look in space, just because you know the exact, even though the model is exactly solvable, like the example I gave. And then we can do some more analysis. This is another example where there's a 2-layered disk. The previous one was 3-layered wedding cake. This is a 2-layered wedding cake, and there's a hole in the middle. Okay, so there's a hole in the middle because of the central potential. So this is how it would look, and somehow each layer gets formed because you start filling the next band in your energy level diagram. Okay, so then it turns out that you can just change parameters in the problem and start creating layers. I can just change the frequency, for example, of the rotation and show that I can just start generating a multi-layered wedding cake. So and here we have some fairly exact results on these kind of phase diagrams. One can show by doing some large analysis that in the bulk of the wedding cake, you can show that these are actually indicator functions with some support. Now you may ask, where is random matrix theory? Of course, one thing is you can think of it as bunch of Ginniber random matrices stacked on top of each other. But then since it's a two-dimensional system, we also analyze these edges here. And we see that these edges are deeply connected to Hermitian random matrices. So I'll tell you what I mean. So this is edge of your wedding cake. So this is a two-layered wedding cake, and this is the edge of the wedding cake. And the kth layer has an edge, and it turns out that the edge of the kth layer has these kinks, and these kinks, the density of the edge, the kth band coincides. The location of the kinks is the location of zeroth of the kth Hermite polynomial, and then you can show that these kinks are related to random matrices and so on. So even though it's a two-dimensional problem, it's an isotropic problem. So you focus on an edge and you start looking for connections to random matrix theory. So and you can also connect it to quantum spin chains and so on and so forth in various regimes. And there is the take-home message is that there is a deep connection between two-dimensional fermions, not only to non-Hermitian random matrices, but also to Hermitian random matrices when you're looking at some edge in the radial direction. And this filling procedure of fermions is a bit complicated when it comes to temperature. I'll not go into the details, but there are we have fairly controlled and exact results where you show that upon increasing the temperature, you basically smear this wedding cake here. I don't know, yeah, you can see some smearing, and we can show that the bulk is robust up to temperatures of order 1, but the edge is more sensitive to temperature order 1/√10. And with that, I will conclude by saying that we computed density profiles of non-interacting fermions in a system and saw some rich wedding cake structure. There's a phase diagram in the parameter space. There's connections to random matrices, polynomials, Tilches problems, and spin chains. And we also managed to generalize it to a large class of potentials of which respect some forms. And I'll leave this future here. Thanks.